All right, so thank you everyone for tuning in today's webinar, API Infrastructure in the Streaming Era. This is actually our first ever hosted webinar at Aklivity, so feel free to consider yourselves pioneers for attending. We're very happy that you're joining us today. My name is Daniel Lukyanov. I'm the CEO and co-founder of Aklivity, and my co-host today is John Fallows, our CTO and second co-founder. We have a lot of exciting things to cover and show you today. We'll start off by introducing Aklivity for those who don't know who we are. We'll touch on our origin story and some of the key learnings from our past life, which form the technical foundation on which Aklivity is built on. Then we'll chat about streaming API infrastructure. What is it? Why it's needed? After that, we'll dive into Zilla, our streaming native multi-protocol agent service proxy. We'll go over features and use cases. There will be many demos throughout the Zilla overview as well. And then we'll go into a bigger demo called StreamPay that really demonstrates the amazing things you can build with streaming native API infrastructure. And lastly, we'll wrap it up with an overview of the Zilla roadmap, covering the exciting new streaming API features that will be coming. And at the end, of course, we'll leave time for Q&A and interactive discussion. So let's jump in. At Aklivity, we are on a mission to make streaming and real-time data processing accessible to every developer. We're doing this by pioneering a new category of API infrastructure that is streaming native, which allows developers to stream via APIs they already know and use. Aklivity is a young company, but as you will see, it's built on years of experience in the space. And the technology is actually a continuation of an effort that began at another venture of ours. We're based in sunny Palo Alto, California. We're proud partners with leading streaming vendors in the space such as Confluent, Red Panda, and AWS. So they say one of the best ways to understand and appreciate where someone is going is to understand where they're coming from. So in terms of our journey at Aklivity, to shed some light on the origin story, I'm going to hand it over to John.
Thanks, Leonid. Yeah, we started quite a while back. Just advance the slide there. Yeah, we started a while ago on this network protocol optimization for the web. I guess must have been well over a decade ago, maybe even 15 years ago or more. So early on in the beginnings of HTML5, when this was when HTML4 was still current, and we had lots of plugin technologies in browsers to try to make them more capable and more interactive. One day when we're working on the HTML5 spec, a new communication section of the spec added something called TCP connection. And the idea there was to make HTML5 suitable for the same kinds of interaction patterns that browser plugins could achieve, so that plugins wouldn't be necessary on mobile devices. And from there, we took the TCP connection and I helped to give it the new name, worked with the team on the HTML5 W3C to work on the name, make it WebSocket, and also to design the JavaScript API there. We were working not only on a JavaScript API, but also on the wire protocol. And we worked on the wire protocol initially in the IETF, in the W3C before it moved to the IETF. And then we formed a working group there that was colloquially called HiBi for Hypertext Bidirectional, where we completed the WebSocket protocol design for RFC 6455. And also, we formalized the integration with the browser origin security model so that you couldn't fake HTTP requests on a raw TCP connection. And we did it all by making it compatible with HTTP 1.1 as it stood, using the upgrade WebSocket approach on the wire. And you might be wondering why there's a picture of a model train down here. It's when the TCP connection API first showed up in the HTML5 spec, the use case that was promoted was remote controlling your model train set from a browser. So as Leon had mentioned, some of this stuff predates Aklivity and our origin story at Kazing. And Kazing is a company that was formed to bring real-time web to the enterprise. And so as part of creating WebSocket, we had to bring that to market in an era where HTML5 had not yet arrived. And so we created Kazing WebSocket Gateway, did many versions of that. I think we finished up on version 5. And that was enterprise WebSocket bringing security and performance and scalability to the market with the Gateway product in order to let customers take advantage of WebSocket even before it was formally delivered. We created an emulation of WebSocket that relied only on what was already available in browsers and sometimes taking advantage of plugins that might be installed too, such as Flash, to make an API in JavaScript that looked and felt like the standard. That let our customers imagine that HTML5 WebSocket had already arrived, and they could fall forward onto the standard as the browser vendors implemented the standard and the end users upgraded their browsers to the most modern versions that supported it. We also took advantage of this full duplex bidirectional capability in WebSocket to layer messaging on top and extend the reach of Java messaging, JMS, down to web and mobile. JMS is not a standard protocol. It's a standard API in Java, and different vendors implement their own protocol. So what it means to extend that is to provide the same APIs in the programming environment. And so we provided JMS-like APIs in lots of different languages like JavaScript, ActionScript for Flash, C# for Silverlight, and also on Windows, Objective-C for iOS, and Java, which was slightly different from standard Java in some ways on Android with the set of APIs that were available to make that happen. So we created all these JMS APIs to the browser so web and mobile app developers could program in JMS concepts. And then Apache Kafka kind of emerged to disrupt all that. And our customers were asking for integration with Kafka as well. And so given that we'd done all this work to integrate JMS, the first port of call was to try to make Apache Kafka adapt that to make it look more like a JMS client so that we could just plug it in and use it. And given the differences between Kafka and JMS, that was a bit challenging. And then also, once you've even done that, you've now got JMS APIs down on the client where application developers are coding, and there's actually no JMS broker in the picture anymore because it's been replaced by Apache Kafka. So that didn't actually seem appropriate. So what we learned from that was that we needed to meet the clients where they are, and they already have their own favorite protocols and SDKs that they would want to use, and Apache Kafka is there on the back. So it turned out that the key approach was to do protocol transformation. And so the Reactivity open source project was initiated to map those protocols together so that they could integrate with Kafka in the back, even though they were using their own familiar protocols on the front. So Zilla is a continuation of that effort. And as you can see, it's built up over many, many years of lots of research and development and advanced techniques for making all these protocols fit together. So what we've really done is we've really generalized the idea of application level protocols above the kernel that everything is basically a stream. We treat everything as a stream. Actually, we treat everything as a unidirectional stream and a pair of unidirectional streams to create bidirectional streams. And so even things like TCP is just a raw pair of streams. TLS has encrypted on one side and decrypted on the other side. HTTP might be decoding raw protocol and have a request response stream coming out of it. In this particular example, we're showing gRPC as it maps across to Kafka. And it's a pipeline of streams that are flowing over shared memory inside the Zilla project. And they each have back pressure. So there's an internal flow control mechanism that allows the different streams in the system to go at full speed, but never overwhelming the next one in line. And that allows us to get good throughput, and also means it helps with latency because we don't end up doing a lot of extra work to build up a lot of buffered data that then has to do extra work to flush it out again. We're always just moving the data that can go seamlessly through the stages in the pipeline and out to the destination in either direction. In terms of implementation, it's implemented all in Java, but it's implemented in what you might call system level Java coding style, where we don't do a lot of object allocation on the data path, for example, and we use a flyweight pattern over raw memory to access it in a strongly typed way. We don't use locks in the code base to make sure that we're always making progress. And we have a multi-core CPU-friendly design, meaning that sometimes the streams need to cross cores if there's perhaps some kind of fan in or fan out scenario going on. And in that case, we have a very lightweight mechanism for coordinating that without requiring any locks. So we have very good data structures in place that can operate at very high speed. The whole design of Zilla is extensible by design. So each one of these pieces in the pipeline, these are called bindings, and it's very pluggable to create a new protocol. In the pipeline, we just create a new binding and map it into the system. For each of the streams in the system, there's the concept of a generic stream and then a strongly typed stream. And the difference between them is just that they have metadata describing what kind of stream they are. So at the beginning of a stream in HTTP, it might include the headers, for example. Similarly, for a Kafka message, might include the headers and the key. And so when we're mapping these protocols together, it mostly comes down to mapping metadata and a little bit about mapping stream lifecycle as well.
Cool. Yeah, good stuff. Bringing back memories from the good old Kazing days. Yeah,
For
it's
sure.
been a while. But yeah, that's great. So that's where we're coming from. And now let's take a look at where we're going. Before we do that, let's take a closer look at streaming API infrastructure in general. But before jumping into streaming APIs, perhaps it makes sense to take a step back and just talk about APIs in general first. So API stands for Application Programming Interface, and it's a software intermediary defined by a set of rules and protocols that allows two applications or services to talk to each other. And an API defines functionalities that are independent of the respective implementation of the two apps or services that it connects. So the reason why APIs are so important is because APIs allow the abstraction of functionality between one system and another. An API endpoint decouples the consuming application from the infrastructure that provides the service. So as long as the specification for what the service provider is delivering to the endpoint remains unchanged, changes to the infrastructure behind the endpoint should not be noticed by applications that rely on that API. So this allows the service provider to have flexibility on service offerings. For example, if the infrastructure behind an API is based on physical servers in a data center, the service provider can easily switch to virtual servers that run in the cloud. APIs, unlike point-to-point integration based on connectors or integration pipelines, are reusable, which in turn directly supports speed and agility, because once an API is in place, it can be used by existing and future applications alike. And related to that point, APIs have a life cycle, so they can be created, managed, and distributed in a controlled and predictable manner that sets you up for success. The most prevalent type of API out there is REST, which stands for Representational State Transfer. And REST APIs are defined by relying on the HTTP protocol to enable a client and a server to get, post, put, and delete data, formatted mostly as JSON and sometimes XML. And REST is great. It's easy to use, it's flexible, it's stateless, scalable, and there's a lot of tooling out there for REST and strong standards to go along with it, such as OpenAPI. And for this reasons, REST has been the backbone of monolith, service, and microservice-based architectures. But REST has a few key limitations. The first is that REST is a fairly crude API where clients may receive more data than they need, called overfetching, or they may have to make multiple requests to gather sufficient information, underfetching. And this, as a result, impacts performance and resource efficiency. More critically, though, REST is not designed for real time because it's based on a request response paradigm, so it's batched in nature. And lastly, REST APIs, particularly in the context of service-based architectures, result in tight coupling between services, which also impacts scalability. These limitations prevent REST from effectively addressing the scale and urgency of digital use cases that have an innate, strong real-time requirement, such as those found in fintech, AI, IoT, and beyond. And to handle such use cases, event-driven architectures and streaming have to be turned to. And in particular, today, modern event-driven architectures have become known as data streaming architectures that are increasingly standardized on Apache Kafka. And for good reason. Kafka brings a whole new level of efficiency, reliability, and performance to streaming scenarios. Kafka is able to do this because it combines messaging, storage, and processing into one. It's distributed by default, and it was designed for extremely high throughput. So data streaming is extremely powerful and unlocks many opportunities, but it also brings a whole new set of API challenges. Firstly, unlike in bashed service-based architectures, where there's a limited type of APIs present, almost everything is REST. In data streaming architectures, there can be a host of APIs, Kafka, WebSocket, MQTT, and even HTTP and REST. Besides the diversity in APIs and protocols found in these architectures, there's also a diverse set of message formats. Kafka services may be relying on Avo, for example, while HTTP clients are JSON-based. The latency requirements are higher inside data streaming architectures because things are expected to process and work in real time. And authorizing and authenticating streaming clients is tricky. In the batch world, there's a natural breakpoint at which security and authorization can be enforced. It's between the request and the response. In the streaming world, when a client is receiving a continuous flow of data, there is no logical point at which to enforce authorization midstream. So this is something new that has to be taken into consideration. And then clients and services are decoupled inside a streaming architecture by way of a broker. So there's no direct line of sight among the services, so service discovery becomes harder. But lastly, perhaps the biggest challenge of data streaming architectures when it comes to APIs is that the client and the server may not speak the same protocol. So in the RESTful world, the client and the server both speak HTTP. But here we see the server is Kafka, which has its own protocol. And the client can be a browser, an IoT sensor, a gRPC microservice that doesn't understand or speak Kafka natively. So API infrastructure helps create, deploy, and manage APIs, but the vast majority of API infrastructure out there was designed for REST. And as we just saw, streaming is very different. So you can't just take existing bashed API infrastructure and carry it over. Streaming API infrastructure requires a whole different type of architecture and approach, which is exactly what we're carrying out at Aklivity. And we're doing this with Zilla. So Zilla, if you're not familiar with the project, is our multi-protocol streaming native edge and service proxy. It abstracts Apache Kafka for non-native Kafka clients, such as web applications, IoT devices, and REST and gRPC microservices. From a technical standpoint, what Zilla really is, as John has already alluded to, is a highly performant, highly extensible protocol translation engine, where it takes a protocol on the client side, such as HTTP, MQTT, or gRPC, and takes another protocol on the server side, such as Kafka, and maps the two together. Zilla's special sauce is that internally it treats every protocol as a stream. So mediating between these different protocols simplifies the mapping protocol-specific metadata. And it does all of this through a declaratively defined routed graph of protocol decoders, transformers, encoders, and caches. You'll see Zilla in action in the subsequent demos. But some of the key highlights of Zilla are, first, it's lightweight and efficient. We built Zilla completely from the ground up. We don't use Envoy, we don't use Netty, we don't use Kafka consumer and producer libraries. Everything is done on the protocol level. Zilla is multi-protocol, so it supports Kafka, HTTP, gRPC, MQTT, and can do mappings amongst these different protocols. Zilla is also multi-payload, so it supports protobuf, Avro, and JSON schemas, and can do inter-payload conversion. On this note, it also integrates with schema registries for data governance. So Confluent Schema Registry, Parapace, AWS Glue, you name it, Zilla integrates with it. And Zilla is designed with security in mind. It has support for enterprise-grade authentication, authorization, and encryption. Finally, one of the things that's really exciting about Zilla and worth highlighting is that it's open API and async API compatible. So you can actually bring an existing open API or async API spec and use that to configure Zilla, or you could use an existing spec for validation. So with streaming API infrastructure such as Zilla, there are a multitude of exciting opportunities that can be addressed. The first is assembling a scalable data broadcasting and notification solution for web-based use cases. The second is simplifying real-time data processing in the context of IoT deployments. And finally, it can be used to unify service mesh and data streaming sides of the architecture to form an event mesh. So let's take a closer look at the first use case, web streaming fan-out. This use case is all about enabling Kafka to become web ready. Kafka is a system that's not designed to be exposed to the internet in a large number of end clients, as found in web and mobile use cases. So what Zilla can do is take data in Kafka and map it to a web streaming protocol called server-sent events, and then use SSE to broadcast continuous updates to web and mobile clients at scale. SSE is part of HTML5 and is supported by almost all of the browsers and mobile frameworks out there. So the beauty here is that there's no client library or SDK from Aklivity or from Zilla that has to be installed. Moreover, SSE is a powerful protocol. It comes out of the box with powerful features such as auto reconnect, which provides message delivery guarantees. So in the case of mobile use cases, if there's a blip in the network, and the mobile device is receiving a stream of SSE messages, and the internet connection drops, the SSE stream will be gracefully reestablished by the server, by Zilla in this case, without any messages being lost by the client. And when Zilla is used for fan-out, it handles connection offloading because, again, as just described, Kafka is not a system that you want to be exposing to tens of thousands or hundreds of thousands or millions of end clients. So what happens is Zilla doesn't maintain the same number of connections coming in from the clients going out towards Kafka. Inside Zilla, there's actually a cache that gets populated with data. And then from this cache, Zilla does the fanning out to the large number of end clients. And within this fan out or within these SSE streams, Zilla also supports message filtering. So different streams of updates can be sent to different clients. Not all clients have to be receiving the same stream of updates. One of the unique enhancements that Zilla offers on top of SSE is something called continuous JWT authorization. So with Zilla, clients can use JWT to authorize and gain access to an API. But as mentioned in the streaming case, unlike in the request response or in the RESTful scenarios, there is no logical breakpoint at which authorization can be enforced. So sure, you can authorize the clients at the beginning to ensure that they have the right privileges to access the stream, but client privileges may change midway through the stream. And sometimes you need to reestablish these credentials midway through the stream. If the client is, their credentials are expired, then sure, you can sever the stream, and that's fine. But if the client's credentials get reestablished, then severing or interrupting the stream of updates results in a very bad end user experience. Imagine if you're an end user and you're following, for example, a sports game, and you're receiving updates on the sports game, and suddenly the app closes down because your client privileges expired. That's not great. So to avoid this, what Zilla can do is actually authorize or reauthorize clients on the fly in the background and ensure that if a client has the ability to reauthorize midstream, that the stream doesn't get severed and the end user experience is uninterrupted. So server-sent event is actually based on HTTP. Unlike WebSocket, for example, that's TCP-based. So besides SSE, Zilla also supports exposing Kafka over more traditional HTTP REST. But Zilla is not just another REST proxy, which is very important to highlight here. It actually enables creating true application-centric REST APIs on top of Kafka, making Kafka look like an absolutely vanilla web REST server, meaning there are no Kafka system level concepts that get exposed to clients, as in the case of, for example, the Kafka traditional Kafka REST proxy. So there's never any mention of topic or partition in the HTTP URLs. And there is support for all of the REST verbs. So clients can get, post, put, and delete to and from topics. Moreover, Zilla can carry out correlated request response over Kafka topics. So it handles the correlation of requests and responses. It also provides idempotency guarantees. And last but not least, Zilla, as already mentioned, is open and async API compatible and can use these specs for both configuration and validation. So for example, if you have an existing open API that you're trying to make more event-driven, you can actually take that spec for that open API, drop it into Zilla, map it to Kafka, and your clients that are consuming this open API would be unaffected. They would still be interfacing to the exact same API. But on the other side, instead of a traditional SQL database and a REST web server, it's going to be Kafka. So with a fairly seamless motion, you now have an event-driven pattern that's accessible to these clients. So I'm going to hand it over to John to actually show this all in action, because a picture is worth 1,000 words, and I think a demo is worth 1,000,000.
Thanks, Leonid. Just take the share here. Okay. So I just wanted to start by saying, so you can see the browser there, Leonid, no problem?
Yep, all good.
Okay, excellent. So just want to start by saying this is the Zilla project on GitHub, and I'm just going to be looking at some of the examples. And some explanations of each one with READMEs to guide you through as you go. So I've cloned that repo locally and open it up in Visual Studio Code. You can see the same list of examples here. And we're going to go through the Open API async API example. The Open API async API Kafka example has a Docker Compose file here, and we can get that spun up pretty easily just by clicking on Run All Services here. So as that spins up, it's just going to wait till Kafka is ready to go. And then while we're looking at that, I just want to show that inside the project for the example, we have two different specifications. We have the HTTP Open API specification, which I think we can open in a preview mode here. For the API, so you can see this is a standard definition of an Open API spec, including the individual operations described with some examples for creating and retrieving pets. And then the Kafka async API is also there. A async API v3 specification that is also able to define different operations. So for those of you not familiar with async API, it's the async version of what OpenAPI started out as for HTTP. And so it covers a range of different protocols, including Kafka protocol. So then if we look at the HTTP OpenAPI spec, and we can see that we can try these operations, and we can maybe I'll try the post one actually. Do a post, and we'll send the post, and it got a response 204. So let's find out what's actually happening under the covers. So we've got Apache Kafka running in the background here on the Docker Compose stack. These are all the services that started up earlier. And then Apache Kafka is one of those. And we have various different topics in here. In this case, we've got the pet store pets topic, which is being used to read and write individual pets. So let's start a consumer here, and then we'll run this. We'll run this again. And so if we send this one more time, we can see that we actually got a record passed in here with headers of content type application JSON. And this is the example payload that it produced for the request. So this is the example that is just generated from trying it from within the user experience. And so you can see from this that the focus on standards integration with specific protocols like HTTP and Kafka allows us to use standard tooling to launch standard APIs with no mention of any of the Kafka-specific concepts in the APIs. And at the same time, we're able to integrate with Apache Kafka and get the messages into the topics, no problem. And then other systems are able to consume the information, observe the information that's sitting in Apache Kafka as well. Back to you, Lena, for the slides, please.
Cool.
Excellent. So I just wanted to quickly talk us through what we saw there. So architecturally, then we have a HTTP client that's speaking to Zilla, and it's perhaps in this case it's doing a put, updating an individual item, and inside Zilla we're mapping that onto a Kafka produce, so that Kafka produce ends up going into Kafka, and then has a correlation ID that goes across to Kafka microservice and is able to correlate that request coming all the way back. One of the things that's kind of interesting about this flow is that when we're integrating with a Kafka microservice like this, we actually don't respond back with the 204 until we've actually got the confirmation of the post into Kafka and get the correlation back from the client, from the service. All right, Lena, I think we're ready for the next one.
Cool, brilliant. So in terms of the next one, next use case is all about IoT. And in IoT, MQTT and Kafka are often brought together. MQTT is used for upstream ingestion, while Kafka is used for downstream data processing. And traditionally, to bridge these two worlds, you would need to run an MQTT broker and Kafka Connect. But with Zilla, the overall deployment can be significantly streamlined because it can actually turn Kafka into a fully fledged MQTT broker, removing the need for a dedicated one. Zilla not only enables MQTT messages to be directly published into Kafka, but it also maintains MQTT client state in Kafka topics, and it cross-maps MQTT and Kafka topic spaces. In terms of version support, Zilla supports MQTT v5 and v3.1, and it also supports Sparkplug B for industrial IoT use cases. This is actually one of my favorite features of Zilla, and I'm going to hand it back over to John to show it in action. You're on mute, John.
Thanks, Lena. Yeah, so you should be able to see my screen again. I just cleaned up the previous one, so we're ready to go for the next one. This is the async API MQTT Kafka proxy example, also from Zilla examples. So we have a Kafka, we have a Docker Compose here, and we'll just spin that up here, ready to go. And we can see from the Docker containers that that's running. Now it's healthy, all good. So now that we've got that up and running, we can actually take a look at the port numbers that we have here. So Zilla is exposing port number 7183 as MQTT. I'll show the config in just a minute. The MQTT client is also going to be connecting on MQTT 7183. And I just want to take a look at the compose file for this. So, for example, if we take a look at the README, you'll see that there's some examples of how to use standard tooling for MQTT to be able to publish and subscribe to the MQTT entry point for Zilla. So we'll grab this particular topic path for MQTT and we'll subscribe to that. And then go back to the README and take a look at this publish. So we're going to publish to this particular topic with a specific value filled in. You'll notice there's a wildcard with a plus here. This is in MQTT terminology. This is a single level wildcard. So any value that goes in there, we've got the number 1 in there. So if we just go ahead and send this message, you can see the messages are coming up, right? So now we take a look and say, let's refresh this and take a look at the topics. Now you can see there's a few different topics in Kafka here. We have a generic set of topics that are used for messages in MQTT, messages that are not retained, messages that are retained, and then the session state, as Leon had mentioned, is also stored in Kafka. You do have, those are the defaults, and you do have the option to put in particular rules that will let you redirect specific Kafka, specific MQTT topic spaces into different Kafka topics as well. So they're not all going into the same one. That's what we've done here for the streetlights. And so if we start up the consumer here, and let me just move that over to the side so you can see that more clearly. Then we can start publishing messages, and you can see they're coming in. So as we're publishing here, there is no separate MQTT broker in play here. This is Zilla making Kafka look and feel like an MQTT broker with all the storage going directly into Kafka itself. So that means when you get confirmation that you've published into MQTT via Zilla, it's actually already landed in Kafka. You're not wondering about whether or not it got synchronized over from one broker to another. It's already in Kafka, and other systems can then react to that immediately. And I did say I was going to show the configuration for that. So if we take a look at this etc directory that has the zilla.yaml, this is the example of the configuration of how we configure Zilla to do what we want it to do with bindings. And in this case, we've also got a telemetry exporter for events to log what's happening. We'll be able to visualize that as well. So if we take this, you can see it's a very simple diagram. We've got the North MQTT server, which is an async API server, using the async API spec that we showed earlier, an example of that earlier. And then we've got the Kafka proxy, which is an async API proxy mapping from MQTT to Kafka, and it's saying which async API defined channels they're called in async API for the storage for sessions and retained messages and messages as well. So channels, you can think of a little bit like topics. They do map onto topics in Kafka. And then the client is using the Kafka spec to understand how to connect over to Kafka and map these things through. So it's a very simple Zilla YAML to configure this. We got an MQTT broker and less than 100 lines of YAML on top of Apache Kafka. So back to you, Leonard, for the next slide.
Brilliant, brilliant, brilliant.
Yeah, so then just briefly then, this is what you just saw from more of an architectural point of view. So you got an MQTT client that can connect in and it'll get a CONNAC back. These are packets in the MQTT protocol. And Zilla is taking care of the MQTT part of that. And the one on the left here is publishing a message into a specific topic, and that's going to land in Kafka by default on that MQTT messages. One thing to point out is that message ordering in MQTT is by topic. And in Apache Kafka, message ordering is by topic partition. So when you read multiple partitions in parallel from Kafka, you might get an interleaving of the messages where the order is not guaranteed. So if you do want to guarantee ordering, the idea is to put messages into the same Kafka topic partition. And the way that that typically works is you set the message key, and then based on the message key, a hash algorithm is used to figure out which partition to put it in. So one easy way to get messages to go into the same partition is to use the same key. And so we use the topic name in MQTT topic name that is, as the Kafka message key when we put the messages into Kafka. And that way, when you publish multiple messages on the same MQTT topic, they will end up in the same Kafka topic partition, and then they will maintain their ordering. And so whenever you have a second client over here on the right that's connecting in as client two then, and it's subscribing, it's going to see messages arriving in the same order as they were published.
Cool. Cool. All right. And then for the final solution that we alluded to is all about gRPC. So Kafka and gRPC are technologies that are increasingly found in the same architecture. gRPC is great for microservices because of its performance, its reliance on protos, and its support for streaming. And Kafka is great for data processing and distribution. So it's natural to want to unify them, and this is something that Zilla enables. So Zilla can make Kafka feel like a gRPC server or client, and it supports unary RPC, server streaming, client streaming, and BiDi streaming. And with Zilla gRPC, microservices can seamlessly communicate through Kafka. They can do correlated request response over topics, or they can just produce and consume data to and from Kafka one way. So again, you guessed it, I'm going to hand it back to John to give you a short demo of how this actually looks like in action.
Thanks, Leonid. I just about got the other stuff cleaned up so that we can do the next one. That's great. Okay, so here we are in the gRPC Kafka Echo demo inside Zilla examples. Once again, we've got a Docker Compose file here so we can run all the services. And they're just starting up now. So we'll see them come up here. So it's very easy to get going here. And then in this particular case, we've got a gRPC endpoint that we've reached in Kafka. I think I'll actually show you the config first in this one, just so you can get a feel for it. So here in Zilla YAML, similar to before, but a little bit lower level because we're not driving it with async API and open API specs on this one. This is a TCP server to HTTP server, the gRPC server. So this is a lot like the example that you saw in the slide deck earlier on with the pipeline. And then a gRPC Kafka mapping over to Kafka going through a cache and then a Kafka client. So this is allowing us to map gRPC through to a endpoint. So actually, I want to not do this one. I want to do this one. Compose. So let me just quickly tear that down. The gRPC Kafka Echo doesn't use the service on the other side, but I want to grab the one that actually does. So we'll go with gRPC Kafka proxy. And in this particular case, you'll see it's very similar to what I just showed you, but actually it's also got a Kafka gRPC mapping as well that will take messages off of Kafka and use them to go and run against a remote gRPC server. Nice little gRPC client in here as well that can we can use to drive. So we've got gRPC hitting 7151, and we're going to use the server streaming. So if I click on this, or we connecting gRPC examples echo, server streaming echo, RPC localhost 51, and this is the request that we're going to send. And when we send it, we get back 10 different messages coming back. So what's really happening under the covers there? Well, if we go look at Kafka and collapse this and refresh it, and we come back into Kafka and take a look, we see we've got two topics on this one, which is the echo requests and the echo responses. So I'm going to open up a consumer for each of these, and we'll move them over to the side, just like last time, so we can see that better. And we'll put them, maybe put them like one underneath the other, like this. Oh, missed. Oh, there we go. Snapping now. Okay, so we've got these two consumers set up. One is going to echo requests, and one is going to echo responses. So now we're just going to send this one more time so you can see what happens. So we sent this, it finished immediately, but here we can see we sent one message into, actually there's two, but there's one message with hello streaming payload going into echo requests. And then on this side, we see 1, 2, 3, you can see 10 messages coming back. And one thing that you might have noticed is that the second message that goes in on the request is actually a null message. And so when we do streaming and we map it into a Kafka topic, we're actually sending a sequence of Kafka messages, and it terminates in a null. And that allows us to detect the end of stream. So that allows us to then map it back into end of stream, and we map from Kafka back to gRPC. You can see that the key here for the messages that are going in is all the same. So we've got from 64 over to CB there on the key. And you can also see that the offsets here are 2 and 3. And the reason that starting at 2 on this one is because we already did one earlier that we didn't show, the Kafka side of it. So that was using offset 1 and 0 and 1. And so now we end up going with 2 and 3. And so here we're coming in with the response messages coming back, and that's starting at offset 11. So that's because 11, and you'll see at the bottom here, 11 through 20 are the 10 messages being echoed, and then 21 is the termination. So prior to this, we had the 0 through 10, 0 through 9 for the 10 messages, and the 10th one was the null terminator. So you might also be wondering, why do we have a null terminator on the side of the request side that doesn't actually have a stream? And that's because in the gRPC protocol itself, you can evolve a unary RPC a single message into a stream, and it's done in a compatible way at the protocol level. So that means that we need to make sure that we can also evolve from single message to stream in the mapping to retain that same level of flexibility on compatibility. And so that's why we model the single message as a single message stream rather than just a single message by itself. One last thing is this is got this funky looking character here in front of the hello streaming. And that's because when I created the consumer, you can see it says UTF-8 record values. So it's just interpreting this value as raw UTF-8, but actually it's encoded in protobuf. And in protobuf, you'll notice that here's the JSON that's going in that's got this message key on the structure, but that word message is not present in the actual protobuf encoded value that's going into Kafka. Instead, this is a marker that goes in front of it in the protobuf encoding to say which field the value that follows describes, and that's what the message here is kind of represented by this encoding, which is showing up as a funky UTF-8 character in the raw presentation. All right, and I think maybe just the last thing to do then is just to quickly show what that gRPC service was on the protos. And let's put it on the big one.
Oh, I grabbed the screenshot, so if you want to
Oh,
go
you already
with that.
grabbed it? That's okay. We'll just continue and go with the share. So the just to look under the hood, we can see what actually happened here. You've got a client that's sending a gRPC request, and under the covers, gRPC uses HTTP2. And so it's making these colon prefixed headers are called pseudo headers in HTTP2 that are sort of reserved names for specific things like the method and the path. And so this post is coming in from the gRPC client and sending some payload. So if you did BiDi streaming, you'd send multiple messages one after the other, and then end of stream. And that's what I was talking about whenever we do multiple messages followed by a null, and that flows through to the target server. And then on the way back, similarly, we get multiple messages and a null value to terminate it. And that's when we end up with the trailers. So this is the flow that we get through Kafka. Now, one of the things that's kind of interesting about this is that yes, there's a gRPC client and a gRPC server in play here at the same time with Kafka in between. But in some cases, PC service on the other side. Similarly, if you have a gRPC service on the right-hand side and you need to call it from a Kafka native microservice, you can switch out the whole left-hand side and publish, produce and fetch messages in and out of Kafka using the same technique and the same headers so that the gRPC service on the other side is also blissfully unaware that it's being called by a Kafka native microservice.
Very nice. So I actually lied. I didn't when I said that the last use case was the last one. There is one more capability that Zilla has, which is very important. But before covering this capability, one thing worth highlighting is that the capability is secure Kafka is secure Kafka gateway that's used to manage native Kafka clients. There's actually two flavors of Zilla, two versions. There's an open source version, which is what we've been looking at, and then there's an enterprise commercial one called Zilla Plus. The features that we just looked at, HTTP, MQTT, and gRPC, they're available in both versions, in the open source as well as in the commercial. Although Zilla Plus has additional integrations with services when it comes for monitoring and security and data governance. But the secure Kafka gateway capability is reserved only for Zilla Plus. So this capability is all about the fact that Zilla natively supports the Kafka wire protocol. So as a result, it can manage connectivity between Kafka clients and brokers. And as a result, it can be used to securely expose a privately networked cluster to the internet. So clusters such as those offered by Amazon MSK or enterprise Confluent Cloud clusters, they run in a private network. If it's an AWS, usually in a VPC, and they're not accessible over the public internet. And Zilla can be deployed in front of these clusters and expose them to the internet over a custom domain. Moreover, the Kafka endpoints that are generated by Zilla that are made accessible to external clients can be further secured against things like DDoS attacks because they integrate with services such as AWS Shield. And one of the exciting enhancements coming to Zilla's Kafka gateway capability is support for virtual clusters and topics, which will allow segmenting groups of clients in a Kafka cluster. There are a few exciting use cases for the secure Kafka gateway capability that's worth highlighting. The first one is partner integration. This is especially relevant in the context of industry integration initiatives such as open banking and finance and TM Forum in the telco space, where there is this push for more event-driven integration. Historically, organizations have integrated over REST and open APIs, but now with the push towards more real-time and more event-driven integration patterns, there is an adoption of async API on top of Kafka as a means to integrate with partners, and that's something that Zilla can provide. The second capability here that's unlocked with the secure Kafka gateway is disaster recovery. So if you're running a Kafka cluster or you're using, for example, Amazon MSK, you can expose it via a custom DNS name with Zilla Plus, and you can use the same custom DNS name for Kafka in a primary region and in a secondary region. So then you can seamlessly reroute Kafka clients in the case of a DR scenario by simply making a DNS record update. And in the secondary region, because the Bootstrap server names are consistent between the two regions. And the last exciting opportunity here that opens up with the secure Kafka gateway is establishing a Kafka DMZ. So this can support connecting clients that are running on premise or in another cloud environment to your privately networked cluster, and being able to do so without VPNs and without any heavy security and integration middleware. So I'm going to hand it back to John. This is the big, exciting demo that really brings everything together and has a cool, fun element to it. It's called StreamPay. It's basically a Venmo clone, a payment app that we've built using the Kafka, or specifically Red Panda, Zilla, and Vue.js. Everything you'll see in this demo is completely supported by these three components. There's nothing else there. So it's really a cool showcase of different protocols coming together and data streams being used to support a use case that many of us have felt or interacted with on a daily basis.
All right. So let's go to the next slide there, Leonid. Yeah, so thank you. So this is the overview just to take a look and see what's coming. So here we've got this Kafka backend that is responsible for all of the storage in the system. There's no separate database in play here. And Zilla's mapping each of the different APIs through to clients, the mobile or web clients, to be able to use them. There's REST entry points that are used for sending messages to the backend through Kafka, and some microservices that are attached on the back as well to handle the logic. But those are Kafka native microservices. And then also we've got some SSE endpoints that are used for delivering updates to clients on the front in a streaming fashion so that they can see the updates that are coming in regardless of whether they're looking at it from the same place where they initiated the change, or whether it's someone else that made a change and they're just observing the effect. So I'm just going to grab the share here and so that demo. Okay, so just starting out by saying this is a different repo under Aklivity and GitHub. It's Zilla-demos, and under there we've got StreamPay. And so what we're looking at here is the same StreamPay example that you can also run for yourselves afterwards if you would like. So I have that opened up inside VS Code, and we do have a Docker Compose stack here for this one as well. You can see that Red Panda is in there, some initialization to create some of the topics, and then some services for the logic, and actually got some simulation, which you'll see as well, which is kind of cool. And then a Zilla mapping here for running the UI and also mapping the APIs through, as we talked about in the diagram. So I'm just going to run all those services. And then we'll see all that come up in the stack. And once everything is up and healthy, looks like we're all good here, then I will open up. Actually, I'll show you in the README so you can see. So in the README here at the end, after preparation, everything is up, then we go to this particular URL to get ourselves started. So this is the StreamPay UI. And when it asks us to log in, it's got SSOs set up. You can log in with whichever one you would like. I already accepted it through previously, which is why I didn't have to explicitly authorize. But here you can see that we've got this UI that looks a bit like Venmo, as Leon had mentioned. We've got some simulated users that are sending and requesting payments from each other in the background. And I currently don't have any money in here, so I am going to request some money. Oh, somebody's going to be something like that. I'm going to request some money from someone took pity on me, I guess. So I'm going to request that, and then also take a look at what people are requesting from me, and so we can make payments here and pay that to them. And so you can see that we are making all of these payments into the system. And one of the things, well, I don't have enough money. Look at that. So I'll pay that later, I guess. So one of the things I wanted to show was what's going on in the background for that, right? So if we take a look at the Kafka in here, this is the one that's using Red Panda. So that one, if we look at the topics, you can see there's some more topics going on in here that are needed for the app, exposing different parts. So if we start a consumer on this one, then I think we'll see some various different activities that are coming through. You can see this is simulated with virtual users. And so we can have different events that are saying a payment was received or requested and the amount that was being sent. So this is ticking over in the background. And each time that that is happening, we are getting, I'll just move it back to activities. We're getting an update shown here. But just to emphasize the standards, what I'd like to do is show you the developer tools. And we'll just get rid of this part and take a look at I'll probably just need to reload so it can see all of it. Yeah. And if we take a look at this one, I'm looking for the SSE one, not this. This one. So this is a server sent event stream. This is to activities. And you can see that there's an extra tab here because it's the standard for server sent events called event stream. And so this is the same events that you're seeing presented up on the screen here are arriving in the server sent event stream here. And so you can tell by the integration with the browser that's all using standard-based approach. One thing to point out is that there's an ID associated with each of these events as they come in. And speaking to the point that Leon had made earlier about seamless recovery, if there's an interruption in connectivity, we send an ID with the event so that if the stream is torn down, say you got a network interruption, and then the browser automatically reconnects, then when it reconnects, it sends the ID of the last message it saw. That allows us to pick up from where the client left off. And that handles race conditions too. So for example, if the server thinks that it sent 10 messages to the client, but only seven of them arrived at the client before that network interruption occurred, then when the client recovers, it'll say, hey, I got up to number 7 by sending the corresponding ID. And that way, 8, 9, and 10, and anything else that happened while the client was away can be sent immediately down to the client to let it catch up. So these are all the capabilities that are built into these protocols that we take full advantage of so that the client can get the best experience.
Cool. Right. Every time we run that demo, I wish getting money was as easy as just making a payment request.
Me too.
or getting pleasant surprises of dollars just coming in from random people.
Right.
I guess unfortunately life was a little bit more difficult. So in terms of roadmap, I know you're probably looking at Zilla and you're already thinking, wow, there's so much there. How could you possibly even have a roadmap? What is there left to do? But in fact, there's actually quite a bit left to do. Streaming API infrastructure is a new category. so there's a lot to fill out. And in terms of our roadmap, there are two axes. There's breadth, so we focus on adding support for new use cases and new connectivity patterns. This is all about adding support for new protocols. And then there's depth, which is going deeper on some of these use cases to reduce complexity, increase usability, and enhance production deployment capabilities. On the breadth side of things, some of the exciting features that are coming are Kafka webhook support. So this is a big one to really, again, bridge the worlds of batched and event-driven. We're also looking to do support for HTTP3. A lot of exciting enhancements there. HTTP3 is something that's been in the works for a very long time, and hopefully over the next few years, it's going to really kick off. Once it does, I think the benefits that we're going to experience all as web users are going to be amazing. So it only makes sense that we embrace that activity and incorporate it into Zilla. The other big mapping that we are going to be working on is GraphQL to Kafka. So this is a big one because today, if you're querying Kafka, you have to get all of the data back. But especially in the age of AI, where you have AI agents and AI agents need to access subsets of data and you can't overwhelm them, GraphQL is a great interface that will allow clients and AI agents, for example, to query only the data that they need. WebSocket, you might be surprised to see that given our background. We've done some work on WebSocket. For example, on the MQTT side of things, we support MQTT over WebSocket. So you could use that if you need to stream over WebSocket down to a browser. But there's some more work for us to do to add full-fledged support and map WebSocket to Kafka. And then last but not least is AMQP to Kafka. So this is important in the context of modernization and helping folks move from JMS, for example, to Kafka. There's still plenty of JMS out there, and there's a big problem and a big challenge in terms of how do you bridge JMS and Kafka deployments. So AMQP, with the help of, for example, the Cupid library, will be a way for existing JMS clients to be able to be interfaced to Kafka via Zilla. On the depth side of things, so the first thing is I talked about Zilla Plus. Zilla Plus today is available on AWS Marketplace. It's coming imminently to Azure, and then it will follow on Google Cloud as well. Besides just being available on these marketplaces and coming with things like enterprise support, when we launched Zilla Plus on a marketplace, we integrated with the native services offered by that cloud vendor for monitoring, for security. So on AWS, for example, we integrate with CloudWatch for monitoring. We integrate with AWS Glue, Schema Registry for data governance. We integrate with Certificate and Secrets Manager for the security side of things. And we'll be doing similar things on Azure and Google. Throttling and rate limiting is a traditional API management capability found in the traditional REST API management solutions. So we're going to be adding that capability as well, but we're going to be doing it across protocols. So you'll be able to throttle and rate limit, not just REST, but Kafka APIs and MQTT APIs. Message transformations are another exciting thing. So we're looking at adding support for WASM and enabling single message transform via WASM. So as messages flow through Zilla, you'll be able to write your own logic in your language of choice and then inject it into Zilla to apply transformations and changes to messages before they land in Kafka. On the security side, data masking is a big one. So especially in industries where there's sensitive data, healthcare, one thing that would be helpful is having control over the different fields in the data as it gets delivered down to a client or coming from a client. So we'll be adding support for data masking for Kafka messages. And then last but not least, adding additional, we're doing some additional work on the encryption side. As mentioned, Zilla has a Kafka cache. This cache is what allows Zilla to do things like connection offloading and fan out. So locking down and securing the cache even further by adding encryption there is going to be another exciting thing that we're going to be doing on the depth side of things of our roadmap. So with that, I'm going to open it up for Q&A. I know we went over a little bit. We went a little bit over. A lot of fun here. But if anybody has any questions, happy to take. No questions? Well, maybe then we can have a. Oh, yep.
I just want to say no question, but thanks for the presentation. It was very interesting, especially the demo part.
Yeah, great. That's the main thing we wanted is to actually show you in an action, not just give you just words to describe it.
Yeah, and then also just all the demos that you saw here today are available and reproducible in your own environment. So feel free to try it out directly as well. And if you have any questions when you're trying it out, feel free to reach us at the community on Slack or in GitHub discussions or things like that to ask any questions and see if we can help.
Yeah, that's a very important point I want to reemphasize is that all of these demos you can run for yourselves, and there should be quite easy to get started with. So if you just visit the Aklivity GitHub repo, you'll find well the examples, so the individual features that we showed on the MQTT SSD, that's actually already inside the Zilla repo itself. So it's very easy to try out those individual capabilities. And then the more full-fledged demo, the StreamPay app, we have the separate repo. You can go there. There are instructions in terms of how to set it up and try it all out for yourself. And then, yes, if any questions, you can find us on Slack. If you go to our website, aklivity.io, there's a link to our community Slack. The whole team is there. John and myself are there, quite active, happy to answer any questions, have discussions. Or you can ask questions, open up issues on GitHub directly. Cool. Well, I think then with that, we can call it a wrap. Once again, thank you folks for tuning in. This will be the first one of many, and we'll see you on the next one.